So the outcome of last lecture was, on one hand, a little bit exciting, because what we did is we took the measurements that we get and we tried to use them as a way of designing controllers to stabilize the system. And we actually know how to stabilize systems. We need that the real parts of the eigenvalues are all strictly negative. On the other hand, the outcome of the last lecture was wildly disappointing because we couldn't actually do it. And the reason for that was that we only looked at the output and not at the full state information. So today, we're going to look at how do we design controllers when we take all of x into account and not just y. So if you recall this picture, what we're going to do today is simply say, you know what? I don't care about y. In fact, forget about measurements. What comes out here is x itself. And then, what can we actually do? Now, obviously, what we need to do, which is the topic of the next module, is creative as a way of actually sucking out x from y. But for now, let's just pretend for a moment that we do have access to the full state information. Well, if we have that, well, first of all, we don't have to worry about y whatsoever. So x dot is ax plus bu, forget about y. Then what we do is, instead of saying u is negative ky, we're now going to say u is negative kx, where k is this matrix of various gains in it. In the previous example, it was just a scalar with a 1 in it, but in general, it can be a matrix. Now, just like last time, we plug this choice of u back into the equation for x dot, and then we get x dot is ax plus bu. Well, u is negative kx. So then we can put everything together in this matrix, a minus bk. And if we call this a hat, we all of a sudden have a new system matrix. And our job is to make a hat as pretty as possible. And in particular, a hat is known as the closed loop dynamics, because now we have closed the loop of the system. We're feeding back the state information into the system, and in that way, we're getting rid of the ax's, or x dot is ax plus bu, and we're getting x dot is a minus bkx. And the control design task, from a stability point of view, is simply pick, if possible, k such that the closed loop system is stabilized. And luckily for us, we now know exactly what this means. It means that the real part of the eigenvalues of the closed loop dynamics, a minus bk, has to be strictly negative. So let's go back again to our simple robot to see how can we understand this in the context of the simple robot. And arguably, the entire next module, module 4, is going to be devoted to this question. How do we pick k such that we can stabilize this system, get the eigenvalues we want, and on top of that, how do we get around this rather peculiar conundrum where we only have y, but we would like to have x, and we're going to pretend that we have x? Well, that we will have to wait for. But for now, let's go back to the robot. Let's note, though, first of all, that u is in r, and x is in r squared, or r2. And in fact, if u is negative kx, it's always useful to write down this kind of dimensional analysis where x is n by 1. In this case, u is, in general, let's say that u is m by 1. In this case, it's actually 1 by 1. Then, from a dimensional point of view, k has to be m by n, because otherwise it doesn't work out. So we have to be able to cancel these things out, and out comes something that's m by 1. So in general, k is an m by 1 matrix, where m is the dimension of the output and n is the dimension of the state. Okay, in this case, m by 1 means 1 by 2. We pick k1 and k2 here. Those are our control gains. We plug it in to the a minus bk equation here. So this is a, this is b, and this is k, right? So if we do that, we get this system. And we perform the matrix multiplication. I would encourage you to make sure that I got the matrix multiplication right by doing it yourselves. But for now, let's just accept the fact that the closed loop dynamics becomes x dot is 0, 1 minus k1 minus k2 x. Okay, so now we have these two knobs that we can tweak, k1 and k2. And when we tweak them, the eigenvalues of the closed loop dynamics are going to move around. So in the next module, we'll be systematic in terms of how we actually pick these k's. For now, Let's just pull some case out of a hat. Oh, and I'm a lazy man, so I'm going to pull ones out of the hat. So let's just try k1 equals to k2 equals to 1. Why not? As a first attempt, at least. Well, if I plug this into my a minus bk equation, I get the following closed loop system dynamics. And let's check the eigenvalues of this thing. So let's write eig in MATLAB or whatever system you want to use. If you do that, you find out that the eigenvalues are negative 0.5 plus minus something, something, something j. What are the real parts of the eigenvalues? Well, the real parts of the eigenvalues, they're negative 0.5. So they're strictly negative, which, of course, is what we needed for stability. So we have asymptotic stability. So we have, in fact, achieved asymptotic stability. Now, the other thing to note is that the fact that we have a j hanging around here, meaning we have an imaginary component to our eigenvalues, that means that we can expect oscillations in the way the system behaves. So we have an asymptotically stable system with some oscillations floating around. And they are, in fact, damped oscillations because since the system is stable, the oscillations are going to become smaller and smaller in amplitude, and as t goes to infinity, they're going to, in fact, go away completely. So if I do this, then here is what it looks like. As you can see, very quickly, we get close to the origin. We overshot a little bit, and this is because of these oscillations. So let's see if we can do something about these oscillations. Well, here's another attempt, completely arbitrary. I'm going to make k1 smaller, which means k1 tells me how much I react to position, and k2 tells me how much I react to velocity. You can almost think of this as a p parameter in a PID regulator, and this as the d parameter in the PID regulator, because p is the position in this case, and d is the derivative of position, which is velocity, and that's what k2 is affecting. Okay, if I do that, then my new system matrix becomes this beast here. Well, let's check its eigenvalues. In this case, the eigenvalues end up being these two numbers. And they're real, which means we cannot expect really any oscillations. And even better yet, they're real and strictly negative. So this is an asymptotically stable system with no oscillations. So this seems like a pretty decent design to me. Let's see what it would actually do to the robot. So the robot, well, it's not oscillating, but it's unbearably slow. So what we saw here is that we actually got rid of the oscillations, but we got a system that was much more sluggish in the sense that it's slow and borderline annoying from a performance point of view. But for now, asymptotic stability is achieved. And what we somehow need to do is to be able to achieve stability while doing other things at the same time. But one thing that is absolutely clear is that some eigenvalues are better than others. And our design of control gains somehow should be reflected by what are good eigenvalues. So some eigenvalues cause oscillations, some eigenvalues cause instability, some eigenvalues make the system respond too slowly, and so forth. So what I want to leave you with now is it seems like state feedback is the way to go, even though we don't really know how to get the state yet, but we will by the end of the next module. And we have to be careful and creative and clever in terms of how we select our eigenvalues. And that's another topic for the next module, which is how do we actually select the appropriate eigenvalues to get the closed loop system behavior that we want.